So today's webinar is on using regression. I did this same webinar in August of last year. If any of you attended that webinar, my intention is to basically do the same webinar again. At that time, I didn't have the ability to record webinars, so we don't have an archive of it. And so I am going to do it again for that reason, so we can record it. There may be some differences from last time, obviously, because I may do things a bit differently. I don't know. But if you did see that one, be warned, you're just seeing the same thing again. So regression is the process of, or is the procedure of fitting a curve to data, usually historical data. So what I've done here is I've started out and I've brought in some historical data. So the data here is the stock price of Apple Computer over the little more than the last year. And I'm just using that as example data. It's nice, easy to obtain data. And so what we'll do is we will fit a variety of curves to this data to understand regression. Now, I'm going to be showing a couple different forms of regression: linear, cubic, autoregressive. So I've set up separate modules for these. And let's just start with the linear regression case, where we want to fit a straight line to the data. Now, in Analytica, when you do a regression, you need to tell it what the basis for the regression is. It's that basis that determines whether we're doing a linear regression, a cubic regression, polynomial regression, or whatever. So it's sort of unlimited in terms of what types of fits you can do using this. It's very general. So in the case of a linear regression, what I'm going to do here is I'm going to drag a node down, and I'll say LR basis, LR for linear regression. And so I'm going to make this a self-indexed table. And what we need is we need a y-intercept, we'll call it B, and a slope, we'll call it M. So those are the two terms of our basis. When we fit the line to the data, we're going to have two numbers, two coefficients coming out, the slope and the intercept. Now, what we're going to do to get the slope and intercept is, for the slope, basically we're going to multiply our coefficient times a constant, 1. Okay, so there's no influence on the data. For the slope, what we're doing is we're using the x-axis for that. So that's my date index. Now, the actual identifier of the date index is actually date 1, because date is a reserved word in Analytica. So when I created that index, I titled it date, but the identifier became date 1, so that it would be unique. So I could enter the identifier in here, and that would give me my basis. It's saying, think of it this way: if you multiply the slope times date 1 and then add the y-intercept times 1, that's your equation for your line. Now, I actually have a choice here. I could use the actual numeric date, or I could use the positional date. Okay? The difference is that if I use position, stock data doesn't occur on weekends or holidays. And so from Friday to Monday, there's a 3-day span there. If I use the date like I have it now, Monday is going to be 3 days after Friday, but Tuesday is going to be 1 day after Monday. Okay? And I might want to do that. Alternatively, I could use the positional date. So in that case, I could put an @ sign in front, which means at position, and that will use the numbers 1, 2, 3, 4, 5, and just number all the dates. And that has the effect of making a Monday occur 1 day after Friday, okay? Because it's just taking the dates that actually occur. And it turns out in stock prices, this is a better way of doing it usually. Okay. So to give you an idea, if I evaluate this, we can look at the basis, and you'll see that the basis basically has a 1 everywhere for the B, and then it's numbering the dates for the day. Okay, so that's giving us our basis for the linear regression. Having set up the basis, we can actually compute the coefficients, do the best fit using the function regression that's in Analytica. So I'll put LR in front because I'm going to be doing several different regressions. So the linear regression coefficients. So the function is regression, and it takes 4 parameters. The first is the y variable, stock price. And the next one is the basis we just set up. Then we need the indexes. So we need the index that indexes the data, and we need the index that indexes the basis. Since I made the basis a self-indexed table, that index is LR basis. Okay? And so I can evaluate that, and we can see the y-intercept and slope that's computed there. Okay? So basically Apple Computer is increasing about 25 cents per day is what that's showing us. Now we can see how we did by creating another variable here. I'll call it LR price, where we'll show what the predicted price is based on our regression. So here, the way you do this is you just multiply your coefficients times your basis and sum over your basis index. Okay, and when you do that, we can plot it here. We have our predicted line. This is the line that the regression computes. We can compare that to the data by selecting the stock price and the predicted price and hitting result. And it says, do you want to compare more than one result? And we say, okay. And then we graph that and just make sure that our horizontal axis is date. And you can see how that regression line compares to the original data. Okay, make that window a little bigger. Okay, so let's call that LR comparison. Okay, and so we've done a linear regression. Those are the steps. So I'm going to take you through those steps again, but this time we'll do it with a cubic regression. So here a cubic is a third-order polynomial, and hopefully this will give you an idea of how this generalizes. So I'm going to go ahead and make an index here to index our basis. I could make it a self-index or a local index, but here what I'll do is I'll make a variable k, which will index our basis. And I'm going to need 4 coefficients for a cubic. I need the constant term, the linear term, the quadratic term, and the cubic term. Okay, so I'll number them like this. So here's what I've done. I've just created an index that has C0, C1, C2, and C3. Okay, so this was string concatenation. We just concatenated C to the numbers 0 through 3. And now I'll create the basis. CR basis. Okay. Yes, and ask questions if you have them as I'm going along here. So was there a question there?
Nope.
All right. So for the basis here, what I'm going to do is I'm going to take our positional date like we had before, 1, 2, 3, 4 for numbering the dates, and I'm going to raise it to the power of CRK minus 1. Okay, so except I want the position of CRK. So at CRK are the numbers 1, 2, 3, 4. It's not using the textual labels, of course. It's using the positions, 1, 2, 3, 4. So at the 0th position, or at the very first number, it's subtracting 1, so that's raising it to the 0th power, and so that would give us a 1 constant. And then in the second position, the exponent there is a 1, and so it's just linear. It's just echoing. You know, the third position, we get an exponent of 2, so we get quadratic. So if we look at the basis here, you can see what's happening. So in the CR0 position, it's 1 everywhere. In the second position, it's just echoing the position. Then it's squaring them, and then it's raising it to the third power. Okay, so that's our basis. And so now we can compute our coefficients for the cubic regression, same way we did before. Regression function. First is the data, then is the basis, then is the index for the data, and then is the index for the basis. Okay? So here we compute these. There's our coefficients for the cubic regression. And to see the actual curve, we can do the same thing we did before, where we sum the coefficients times the basis and we sum that over the basis index. Okay, and I'll go ahead and select that and stock price and graph them together so we can just do the comparison. Okay, and there you can see how the cubic fits the data. Okay, so that's the best fit third order polynomial. All right, so let's go ahead and name this one CR comparison. All right, so you guys understanding that? I'm going fast, but
yeah, that's good.
Yeah, it makes sense.
Okay, good.
Yeah.
Okay, and if I'm losing anybody, slow me down, ask questions. Okay, because now I'm going to go into a more difficult one, which is the autoregressive regression. So the idea here is what we're going to do is on a given day, we want to use the previous 10 days of the stock price to predict that day. Okay, so if you're trying to predict what the stock price will be tomorrow, you're going to take today's price, yesterday's price, up to 10 days back. You're going to fit a line, use those data points as your basis, and we'll use a linear fit to those to predict tomorrow's data point. And so if you think about that, if you take all the historical data, each day in that sequence, starting with the 11th day onward, we have a data point, right? So you take the 11th day, there you have a set of 10 input variables. You're predicting the 11th variable from it. And then on the 12th day, you have another data point, 10 input variables, 1 day to predict, and so on. So it's kind of like each data point here where we have 10 input variables each time we're predicting the 11th, or day like that. So what we need to do is basically assemble that data set so we can do a regression against it. So and compute what those coefficients are. So I'll say window size is 10. We want to go back 10 days. Our autoregressive basis, okay, what we're going to do here is we're going to say use the previous 10 days. So this will basically be our basis where 1 means 1 day ago, 2 means 2 days ago, up to 10 days ago. Okay. However, in addition to that data, we also probably want a constant term in there. Okay, we'd like to have one more term that's just like the y offset. Okay, because regressions without the constant term often are kind of don't come out too good. So I'll use the 0 position just for the constant. Okay, so that's our basis. We're going to have actually 11 terms in our basis, the constant term and then the 10 previous stock prices. Now, I'm going to use a different date index because we can't do any prediction for the first 10 days. We have to start with the 11th. Okay, so just pretend the first 10 days don't count as data. So I'm going to just make a new date index that excludes the first 10 days. I'll call it AR date. Okay, so it'll just be a subset of our original date, our original index, where the position is greater than window size. Okay, so let's see here. I should probably make that a date, and let's see if we got it. So it starts, instead of starting January 3rd or whatever, it starts January 18th. Okay, and so let's see here. We want to use that index instead of this one. So let's see here. Okay, what I want to do here is let's go ahead and come up with our basis. So again, what we're going to want to do is we're going to use the previous 10 points each time. First of all, if we have that 0th term, then we want to have a constant 1. Okay, otherwise we want to basically use the previous 10 data points. So I'm going to take the stock price and at a given, it's indexed by date 1, right? So I want to take that date and I want to shift it backwards 10 days. except I only want to do that actually for the AR date. So what I'm going to do is I'm going to say, where does this AR date occur? What position does the AR date occur in that original index? Okay, so our first date occurs at the 11th position, for example, so it would be 11. And then I'm going to subtract our offset. So and then go back that many days. So that would, the right side of the equal sign there would be the position of the date that I'm going to use for my data. Okay? So let's see what that looks like, the result here. So on January 18th, let's do this. Let's put this up here and put our original stock price up here at the same time in table form. Okay. So on January 18th here, you can see January 18th is right here. You can see that it has a constant term for the 0. And then one time period back, it says 94.95. Well, that would be the price at January 17th. 2 time periods back, 97.1. That's the price on January 16th. Okay, and so on. And if you look on January 19th, you can see everything's just kind of shifted. 1 day back, 2 days back. So if you study that, you should see what we've done here. So understanding the basis here, what we're saying is that to predict the stock price on January 18th, these are the numbers we're going to use. Okay, they're the previous 10 days plus a constant. On January 19th, these would be the numbers we're going to use. Okay, so that's our basis for an autoregressive regression. Okay, now that's kind of complex, but it's fun to play with too. You'll find if you get into it. So with that now, the rest is stuff we've seen already. So we can compute the coefficients using the regression function again. Okay, now, there's one little twist here though. Our basis, let's go back and look at our basis before we do this. Our basis is using our AR date, right? So stock price is using the original date index. So what we really want to do here is we need to use the re-indexed stock price. Okay, so I'll say AR stock price. Okay, so basically we just need to re-index and just use only the stock prices that are in our AR date. So we're excluding the first 10. Okay, so with that now we can use those stock prices with our basis. The AR date is now the index that's indexing that data, and ARK is our basis index. Okay, and so here are our coefficients. So you can see that the price, there's a certain constant term, but then the price seems to depend quite a bit and in a positive way on the previous day, and then after that there's various adjustments. Okay, you can imagine the second day, the difference between second and first day is sort of giving you a slope effect and so on. Okay, so let's go ahead and see what that predicts. Okay, so again, it's the same kind of thing. So here's the AR price. Whenever you do this, we're going to just take the coefficient times the basis, summed over the basis index. And I can go ahead and compare that to the stock price and graph it, pivot, and the blue line is the predicted value and the red line is the actual value. Okay? So it's not too surprising those are so close together if you think about it, because we're predicting each day based on the previous 10 days. It's not going to change that much in one day. Okay? So we've done that again. Now we're going to get into some interesting stuff. Okay, so what I've showed you here is we have fit 3 different kinds of curves to the data. In all cases, we did the same thing. We used the regression function, showed how if you just sum it, basically a dot product of the coefficients and basis, you can get what the predictions are on your original data, so you can compare it to the original data, and that's that. So really, you can do lots of different kinds of regressions this way. The key is that the functional form that you're fitting to your data needs to be linear in the coefficients, but each term in your basis can be highly nonlinear. Okay, that's something you can realize. You can have arbitrary terms in your basis, as long as they're combined linearly, and then it fits it. And the regression function in Analytica is very robust. So there are some degenerate cases that happen in regression, like where you, if you have two redundant terms, basically the same term twice in your basis, the coefficients are not uniquely determined because you could shift the weight between them arbitrarily. Okay? And that will cause singularities in simple regression algorithms where things will blow up. But Analytica is robust to that. And there's other situations like that too, where, for example, if one basis term is a function of several of the other basis terms, you also have a degeneracy like that. And Analytica, again, is robust to that kind of thing. So you can throw lots of basis terms in there, and it'll still do something sensible. So you don't have to worry about those kind of effects. Okay, now that we fit all of these curves to the data, we can look at some other concerns that come up with regression. So because we're only using a finite amount of data, in this case I think it's about 350 data points, there's uncertainty in the coefficients we're coming up with. Okay? Because if you imagine the data is being generated by some random process with noise, we get some random points, from our underlying process, and we're trying to figure out what the coefficients of the underlying process are. Well, with a finite amount of data, our estimates of those coefficients are uncertain. And plus, there's this noise term. So we'd like usually to actually look at what the effects of that uncertainty are on our predictions. That'll give us an idea how that finite sample size is actually affecting our predictions and prevent a lot of weird things. So I'm going to add a library here to our model that's called the Multivariate Distributions Library. And it has some functions in there for doing regression fits that give us the uncertainty. So going back to linear now, we're looking at the linear again. First of all, I should mention that one measure of fit that is often used in statistics textbooks, when you look at this, you say, how linear is that really? Okay? And so people use the R coefficient. You've probably seen that in statistics books, which is just correlation. So if you want to compute the R coefficient, you just use the correlation function. So it's the correlation of, the Y value, which is the stock price, and the X value, which in this case was our positional date 1. And we want to do the correlation over the date 1 index. Okay, so the R value in this example is 0.74. Okay, so that's one measure of how good that fit is that you often see. But now a little more interesting is, first of all, when we compute these C values, there's this uncertainty in these C values. The more data points we have, the less uncertainty there is in this coefficient. If we were to do a linear fit off of 2 data points, and we knew that those 2 data points were generated with noise, then we wouldn't have much confidence in our coefficient because, they could have been all over the place. But if we have 1 million data points, we'd be pretty confident. So there's this function called regression dist. Just add dist to it. It takes the same arguments as regression. And it's a distribution function. So it's like regression. If we evaluate it in mid-mode, you'll get the same results you did with regression. Okay? There's our y-intercept and our slope. But in probability mode, if you look at any of these other views, we actually get a distribution. So we can look at the density, for example. I'll graph it and look at one of these at a time. So here is the distribution on our y-intercept. It shows sort of the actual confidence we have in our y-intercept. It shows that it's around 90, but there could be an error of about 5. It looks like maybe up to 8. Okay, so that shows you your distribution on the y-intercept. Similarly, on the slope, there's the distribution for the slope, showing the uncertainty in our parameter estimate. Now, these estimates for these coefficients may also be correlated. So if we look at the sample view here, we can plot these as a scatter plot. And what's nice is to go into the XY graph here and compare them with a comparison index, the basis index. So here we're comparing M is on the Y index, and B is on the x-index, and you're seeing a scatter plot showing the distribution of B and M. So you can see that the estimate for those is negatively correlated. So if we are underestimating the y-intercept, we're probably overestimating the slope. Okay. Now, a second thing is that each data point that was generated, if we imagine the stock price was being generated by a linear process with noise each day, we could figure out what that noise is, estimate what that noise is. And so if we assume it's the same noise every day, there's another function in Analytica that's called regression noise. And so first of all, I'll compute this in a variable called LR noise. Now it takes the same parameters here as the regression and regression dist function, so I'm just going to copy paste and change the name. Okay, and what this does is if I evaluate it, it gives me the standard deviation of the noise process. Okay, so it says we have each day basically there's a noise of $22. Okay, so now I'll mention one thing is there's an optional parameter to this function, which is the C value. Now, in this case, it computed the noise pretty much instantaneously, but to do that, it had to recompute the C value internally. So if I provide that optionally, it doesn't have to recompute it, and it can speed things up a little bit. Like I said, in this case, it's so fast it doesn't matter, but it will produce the same result. Okay. Now, since we've estimated the noise, we can now go in here, and we can add that to our form. So we have our sum of the coefficients times the basis, and now we can add our noise process. So a normal, zero mean normal process using that as a standard deviation. And now we have a probabilistic estimate here for our prediction. So if I look at this in a probability view, like the bands view, here we're seeing the probability bands of our estimate. So no longer is it just a single line regression. We have the confidence levels as well. So there's a 90% chance that the stock price is between the outer two bands and a 50% chance it's between the inner two bands. When you look at the when you look at the comparison, thank you. Here's the comparison. Look at it in bands view now. And the trick here is, notice we have probability as the key, but we want to show both the stock price and the predicted stock price together. And so up here on our comparison, where we can choose between stock price or LR stock price, I'm going to choose all. And it puts both of them on there together. And so here you can see how those bands compare to the actual stock price. And it should be that about 90% of the time it's between the outer two bands and 50% of the time it's between the inner two bands. Okay. So just let's go into cubic regression, and I'll just kind of repeat that process. So really all I'm doing is I'm substituting regression for regression dist. I'm going to estimate the noise process here. Actually, let me just copy-paste the function there and just change its name, noise, and I'll add the CR term in there, and then I will just put in our zero mean noise process. Now I'll mention an equivalent way of doing the zero mean noise process is this way, is to, instead of adding it, you could use the predicted line as the mean, okay, and then the noise is the standard deviation. And in some ways I think this notation is a little clearer, but I don't know, it's up to you. There's other forms of regression that sort of match this style of notation, so it's nice in that way. So now if we look at our comparison, select bands view and all here, then once again you can see the probability bands and how that compares to the data. And you can kind of look at this and say, you know, I'm not advocating that fitting a cubic to stock data is the best way to predict where that stock is going. You can obviously see some downsides of that, I think, just by looking at this, but that is the best fit. So, okay, and we can do that with the autoregressive case also. If you see it a few times here, it should become second nature. So again, just change it to regression dist and estimate the noise. Okay, so copy and paste and change this to noise. Okay, and for the price, once again, just put that standard deviation in there. Okay, and we can look at the resulting graph in bands view. Do the all. Okay, and that one's a little harder to see because the bands are pretty tight, but the stock data is interleaved inside there. And one downside of this little method of using all is that it's using the first graphing color there, the red, in both cases. But okay, all right. Now that gives you a way of using a regression as a distribution. So you've incorporated the uncertainty in your regression also. So analysis downstream that use that regression also reflect that sampling uncertainty. All right. Now, going back to linear again, what we've sort of assumed when we're doing this regression is, showing you the graph here again, is that we're assuming that the underlying process is linear and that each day there's an independent noise added to it. Okay? So it's bouncing around that expected value, or that median value, whatever you want to call it, independently each day. So whenever you do a regression, you're assuming some kind of underlying process like that. You might ask, well, how good of a model is that? And the R value in the linear case was one answer to that. The R value only applies to the linear case. For more complex regressions, we might need a different metric to say how good of a model is that. So one metric we can use is called what I call the fit probability. And so we can ask this question. We can say, if the underlying data really is being generated by the model we're assuming, what's the probability that we would get a regressive fit that's as bad or worse than the one we just got? Okay? And so that gives you kind of a confidence level. The higher that probability, the more confident we are in our model. Okay? So I'll call this LR confidence. So I'm going to just write that down here. So the probability that the regression fit obtained would be as bad or worse than what we just obtained if our assumption that the data is generated by a linear process with IID noise is correct. IID is identically and independently distributed, right? Okay? So that's our confidence level. I'm going to edit this in the attribute pane here. So there's a function that takes the same parameters again that we've seen before for regression dist. It's called regression fit prob. Like the noise process, it can take two optional parameters, which saves it from having to recompute everything. So I like to put those when I have them. Okay, it can take the C and the noise that we've already determined. If it doesn't get those, it has to recompute them. But with that now, this will give that probability. So it's saying there's a 0.5 probability that we would have obtained a regression fit as bad as the one we obtained if our model was an accurate depiction. So that's a number you can make some sense out of. Okay, and you can certainly use it to compare different models. Okay, so out of curiosity, oops, don't close on me. Okay, out of curiosity, let's save. Let's do that for the cubic regression, see how it fared. Okay, so again, I'm going to just copy-paste one of these functions here and change the name to fit prob. And I'll go ahead and add the noise in there. And it's a little better, but Not much.
Nothing's on the screen there, Lonnie.
You're not seeing 0.54 on the screen?
No, it stopped when you created the node. That's it.
Has it stopped for everybody?
Okay, it's back now.
Is it? Okay. Network glitches, I guess. Okay, so the confidence here is about the same as it was with the linear, just slightly higher. Okay, and we could look at the autoregressive one and see how it fared. So again, I'll take one of these, copy paste it, so I don't have to type everything again. I'll add in my noise. So, and I need to change the name of the function. And that one's a little bit better, so 0.65. Okay. Now let's do one more thing here. Let's project into the future. So we've seen how this data, for example, here's the cubic case. We've seen how this data fits, or how our fit compares to the actual original data. But how's it going to do in the future, you know, when we generalize? So what we need to do here is we need to introduce a new date index that extends into the future. Okay, so date 2. Let me see if, okay, so we'll call this one date 2. So what we'll do is we'll concatenate the original date index, and then we'll add to it. Okay, so I'm going to add from the last, let me pull off the last date in our original index. Okay, so that's slice of date, comma size of date is picking off the last date in our first index. And then let's just add the sequence 1 to 100 to that. So we're going to add 100 days to it. And let's do that in units of weekdays. So it's just going to add weekdays. We're not going to put weekends in there and stuff. All right. And I missed something here. What did I miss? Concatenate, date add, and I'm missing a parenthesis, I guess. Okay. Let me format that as a date and show the result. Okay, so we have our original date index, and it's going up now to September 2008. So into the future. And then let's, what else are we going to have to do here? We're going to have to, okay, well, let's go over to our cubic basis here. And we should have enough to do this. So I'll say CR future price. Okay. So what we need to do to extend this in the future is we need to recreate our basis, but this time the basis has got to be on our future index, our date 2 index, okay, instead of the original index. And it's got to include our independent variables for those future dates. Okay, so I'll do it as a local variable here. So I'm going to compute it the same way we computed the basis for this, but I'm going to use date 2 instead of date. So if you remember, we did this, right? That was our original basis. And now with that, I can just put in our predicted form here. So it's the coefficients times the basis summed over the basis index, and then we have our standard deviation for the noise. So we're using the coefficients that we got out of our regression, of course, in predicting the future price. And then the other thing we should do is we should reindex stock price so we can do the comparison. If we were to compare this one and this one right now, they're not really comparable because future price is using our date 2 index, right? See if it computes right. Yeah, it's using date 2 index. And stock price is using our date 1 index. So what I'll do here is say future stock price. And all I want to do here is I want to reindex it, changing the date 1 index to the date 2 index. So it's just going to be the same prices, it's just reindexed. The problem here, of course, is that the date 2 index contains values that aren't in the date 1 index. So if I evaluate this right now, I get a warning. Okay? Never hit this ignore warning button. I tell people that. I hate that button. Don't hit it. It turns off warnings, which is bad. So instead, cancel and go back and just surround the thing with ignore warnings. Okay? Because I'm fine with that warning. I just want to ignore it. What happens now is way down at the end is it's just basically has nulls wherever I didn't have data. Okay? So it has data up till yesterday and then nulls from there on. Okay? So now what I can do, I'll make an alias of this and move it over to our module here. Now what I can do is I can compare our predicted to this stock price like we have done before, graph it, and so on. There we go. And more interesting, let's look at the bands view. Okay? And so you can see there how the future prediction fares. And why does that look like it's doing so bad? In fact, it's going negative. Well, a couple reasons, right? One is our underlying model for the stock price is unrealistic, right? That's really not how the stock price is being determined. So this model obviously doesn't generalize very good. You can see it's bad. Now it's going negative also. That's pretty bad. If you really wanted to do this stuff on a stock price, you'd be much better fitting the logarithm of the stock price. You know, that's actually usually a better way of doing it. But again, this is just serving as data for us. Okay. So. Compare. There we go. All right. So let's go ahead and see how the autoregressive is doing into the future. Now, the autoregressive, if I can get it double-click. Come on. Something's weird here. There it goes. Okay. Now, what's it mean here to project this into the future? Well, as we go into the future, we're going to have to predict tomorrow's stock price, and then the day after that, we're going to have to use that prediction plus the previous 10 days to predict this next stock price after that. Right? And we're going to have to continue like that. So we're going to have to, at some point, we're going to have to start using our predictions to make the next prediction. Right? The way it's autoregressive. So one thing we might do is we might actually decide what date are we going to stop using actual values and start using our predicted values. So I'll put a begin forecast date here. I'll format it as a date, and we'll pick some date here to start at. Why don't we go back a few days at least, April 1st. Okay, is there a question there? I can hear someone saying something. No? Okay. Again, if you guys have questions, I'm going fast. Slow me down. Okay, now what we have to do, though, is we have to re-express that basis in order to be able to make the future stock price prediction. Okay? Actually, here we have kind of a chicken and egg thing. We can't just figure out the basis and then do our sum of the coefficients times the basis, because we need to actually figure out the basis for tomorrow, use that to predict tomorrow's price, and then use that price to figure out the basis for the day after that, right? Use that to figure out the price, and so on. So we have to do them together, okay? So let's do that. This is going to be kind of complex. So first of all, let's store our predictions in an array Y. Okay, that will be our actual predictions. And up to beginning forecast, let's just populate that with the actual stock data. So we'll just copy the actual stock data, the historical data, up to begin forecast, and then from that point on, we'll start using the previous data points. So for the first 10 days, we're going to use some original data, and then after that, it's going to be all based on our predictions, right? So I'm going to do this subscripting again that we did before. I'll use our AR stock price. And what I'm going to do here is AR stock price is let's see here, is indexed by AR date. Okay, So we want to change that over to our new date. Okay, so we'll go ahead and populate it with just the data. But then we're going to start looping over each day that we want to predict. Okay? So here I want to express the days I'm going to predict. I'm going to use positional days. Okay, I'm going to say, because then I can subtract easy, right? I can subtract 1, 2, 3. So I just want to make a list of all the positions, the position of tomorrow onward in that date 2 index. Okay, so if you did subset of date 2 is after begin forecast. Okay, that subset, that would be the subset of days that we want to predict. Okay, but it would be the actual dates. So I want the positions. I want to do this by positions. Okay, so this operator here gives me the positions of those in the date 2 index. Okay, so there I go. For each of these days now, what I want to do is I want to figure out the basis, compute the regression, and put that in Y. Okay, so what I'm going to do is, remember, our 0th element of our basis here is our constant, right? The Y offset, so to speak. So I'm going to start by just populating our current value with 1. That's, remember, the value for the basis. And then I'm going to construct the basis like this. I'm going to say, looks like what we did before. I'm going to say, we're going to go from our current position, take the previous 10 items, it's indexed by our ARK, okay? And so now the basis is all the values in Y from the current day back 10 days, and includes the 0th date, which we've made a 1 here. Okay, so it has all those previous predictions we've made. Okay, and now that we have that basis, we can actually compute the prediction. So we use the same form we had before, where we take the coefficients times this basis, summed over the basis index, and I added in our noise process and all that stuff. And that will predict our next data point. So what I want to do is I want to actually put that in our array. Okay, I'm getting an echo. Somebody has a speakerphone on. Okay, put that in our array like that. So when we finish this iteration of the for loop, we've just populated today with our predicted price, and then we can go on to the next day using that price to predict the next date after that. And when we're all done, I'm going to return Y. That's going to hold all those values. Can you believe that actually took it? Okay, so that's pretty complex, but again, that's how we can predict into the future. Let's see if it works. So okay, so for the first few days there, it looks like we were unable to make the prediction, but after that, that's because the stock data we were using didn't include that data. That's fine. Okay, so looking at the bands view, there it goes from our predicted date. So you can see here our uncertainty kind of spreads out as we get farther into the future, which is kind of a nice property. And we could compare that to our future stock price. So the easiest way I can't really select two objects in there if they're in different modules, so I'll bring that over here. Select them both, hit result, look at the bands view, graph it. Horizontal axis is date. We want to show everything. And so here we can see, now I made our begin forecast at April 1st. So you can see how the price is fitting within those bands for a little while, and then it goes into the future. Might be interesting to bring this beginning date, say, back to October 1st. So what I'll do here is I'll just switch our beginning forecast to October 1st. And let's recompute that result. Okay, that's because October 1st, 2007. Try that again. Okay, and so there we go. So we're starting our forecast. So remember, after October 1st here, what we're doing is we're using our predicted values, our 10 previous predicted values, to come up with the 11th day, right? And so our predictions are being based on our predictions, and that's why our uncertainty is spreading out as we go along. But that model doesn't look too bad now, does it? It's actually sort of containing the actual stock price fairly nicely in those bands. So, yeah. Okay, so that's a good stopping point, actually. Okay, let me just review real quickly. Went over several different things here. So first of all, most important thing about understanding regression is this idea of constructing a basis. So we saw how to do a linear basis, a straight line case, and how that generalizes to something like a cubic. You should be able to generalize that to arbitrary polynomials easily enough. And autoregressive. There's a lot of other types of forms you can come up with as well that fit within that paradigm. But then I showed you the distribution aspect. Because we have a finite amount of data, our parameter estimates are uncertain. So we can actually use the regression dist function to find out what that uncertainty is in the parameters. If your sample size increases, that uncertainty will decrease. Second thing is we could use the regression noise function to estimate what the data point noise is. There's some noise that's making it deviate from its basic curve on each data point. So that estimates that noise, which then gives us a nice probabilistic estimate, complete probabilistic estimate of our prediction. We've seen how you can take those predictions, figure out what real easily by multiplying the coefficients by the basis and summing over the basis index. You can figure out what the predicted value would be for each of your data points. And then we looked at extending those predictions into the future, which is really just re-expressing your basis into the future. The autoregressive case is a little complex because our basis depends on our predictions. The basis is needed to make our predictions, so we had to do that one in a loop. But non-autoregressive cases is fairly simple. You have to just sort of re-index on a future index and use the same kind of expressions. So gives you a few things to work on work with for your data analysis, and that's that. So any questions?
Yeah, Lonnie, I'm sort of impressed by how much slicker the statistics package is now than the last time I looked at it, which was a couple of years ago. Have you written up a little primer section that might be on the web or anything for people who are very rusty or not very familiar? Because you can do a lot of these things now really slick and fast.
Yeah. Let me peek real quick. I can't remember if I put a page on there or not. There may be a little primer. Let's see. So, well, the page on regression itself talks about a number of things. And, yeah, I don't know. This webinar may be the archive for the time being.
This is actually probably a little advanced. I'm thinking about students here, but of course, students quickly become better than professors. But there's some hand-holding below reference manual material. Even like basis functions and things are not all that intuitive until you've been through statistics. And the notion that you can do multiple regression that's really just a linear regression in disguise, and then how do you move these indices, which was I thought very slick today. How you would move from past date ranges to some that included some of it but not all of it. This stuff is non-trivial.
Yeah.
For people who are not facile.
Yeah.
And yet it's really pretty powerful. But anyway, the answer is that you haven't yet, but the webinar is a start. And, and this is on the webinars that are recorded are now on the web?
Yeah, they're archived in the wiki.
Okay.
So
as you can tell, I'm a little behind on that.
Yeah. So good. Yeah. There's a lot of stuff here, and so you're right. Going through this with a very introductory slant to it, that's describing all these concepts in detail. Even though a lot of these concepts overlay basic array abstraction concepts, having a primer like that takes you through each of these anyway is a good way to cover those other concepts as well. So it's a good idea.
As an example, a lot of people use Excel for things of this sort, but there are a lot of again, there's a lot of powerful tools in Excel, but it's actually, you have to do a lot of setup to make sense of it.
Yeah.
And so I think there's a competitive advantage here that once people buy into it, they can see it.
Yeah, that's true. Yeah, there's also another set of pages in the wiki that's called Excel to Analytica Mappings. And on those pages, we've gone through, it's not entirely complete, but it's probably about 85% complete. We've gone through and listed all of the functions in Excel and shown the equivalents in Analytica. So it's fairly concise in each case, but it's another case where if you know the function in Excel, it gives you a quick equivalent expression in Analytica. So things like intercept.
Where is that, Lonnie?
It's on the wiki. It's Excel to Analytica Mappings, it's called. And if you go into, I think, modeling concepts off the very first page, let me see here, our Analytica Modeler's Guide. If you go to Analytica Modeler's Guide, there's a link inside there to how to translate Excel spreadsheets into Analytica, and it takes you into that. And so then in there, for example, there's statistical functions, and functions like intercept are in there, and I think there's slope. So if you did a linear regression in Excel, you'd call each of those functions separately, and you'll see that the regression function. Uh-oh. Can anyone else hear me? Is everybody hearing that? Did I just lose the phone? Okay.
Lonnie.
Okay. I don't know what happened. The phone just suddenly started making a dant sound like something went wrong, so I don't know.
So can you repeat your question, sir?
I'm sure. I sent a little question and answer through on the GoToWebinar, and what it basically asked was, at what point do we need to go to nonlinear perspectives of looking at data? And if we have to do that, why would we, and what's the simplest next step beyond linear?
Okay. So, yeah, that's the question. I think you'd have to bring domain expertise to bear on that. I don't know if there's a general answer to that, but when you are looking at problems in particular domains, you often have a reason to believe that a certain functional form is appropriate. And so that's that's really the rationale. One thing that you need to kind of keep in mind is, as you expand the space of possible functional forms that you're considering, you run into a greater risk of overfitting. Okay, so overfitting means that you have too much model complexity essentially for your data, and that means that even though you may get a really good fit to your data, you'll get a really bad fit on data you haven't seen yet. So you want to avoid overfitting in that sense. And so often the best rule is keep it simple, because once you really start exploring more and more models like that, you may think you're doing better and better on your historical data, and you're actually making things worse as you're getting more complex. So yeah, keep in mind that in the regression case here, you can get a lot of nonlinear effects in there as long as you can identify the nonlinear term in advance. But yeah, I don't know. Often what you find, though, is just that you're coming up with your analysis and your model through some sort of domain-specific rationale or analysis or something, and that's where it comes from. That's why it's nonlinear. So,
is there anything in doing a linear model that would be a red flag to indicate that's the wrong view of the data you're looking at? Like if the R value or the distribution, something gets way out of whack and it just seems to be all over. Is there anything that would be a really good warning sign that the wrong technique is being used?
Well, just those metrics that I showed. So the fit probability is the general one here that applies to all of these models. So if that number starts getting small, then you should definitely start worrying. But it's kind of an art. I don't think there's anything real specific. So like as you saw when we looked at the cubic regression, there's just something about this view, right? See our comparison here. There's something about that view right there. When you look at the right side, you can see the trend there, where your prediction's going, and you can see where the data's going. And it's just pretty darn evident just by looking at it that something's wrong there. But, since the computer's looking at that data as if it's sort of independent each step of the way and so forth, it doesn't really detect that at all when we look at those coefficients. So, you got to look at things like that. There are actually some statistical tests for independence. So you can look at, how autocorrelated the data is to previous data points. That's, one way to test that particular assumption. We didn't actually test that during this webinar. But in general, I don't know. It's not an exact science. So another couple tricks actually.
That answers my question, though. I'm not missing anything obvious then, and I appreciate your feedback.
Yeah. I will mention one other thing that's very common, though, which is cross-validation. So what people will do is they will fit a subset of their data, like maybe 2/3 of their data, and then they'll use the remaining 1/3 of their data to test how good that fit is. And so since you didn't train on that other 1/3 of the data, it gives you some indication of how good or how bad you're doing. So in a case like this where we're doing linear, you might use the first 2/3 and then test on the remaining 1/3. And if that comes out really good, then you might say, hey, I might have a pretty good model here. So, okay. Any other questions before we wrap up? No? So, thanks, everybody.
Thanks, Tony.
Okay.
Great. Thank you.
Bye.
All right. See you all next week. Bye.
Mm-hmm.